Thank you all for coming, and welcome to the joint session in Geophysics and Hydrology in High-Latitude and High-Altitude environments, and the candidates for the Chevron Award for Best Student Paper in Seismology. So I'm Andrew Fredrickson from the University of Manitoba, and I'm co-hosting the first part of this, which will be the Chevron Award papers, and along with Yajing Yu of McGill and Andrew Ireson from the University of Saskatchewan will be taking over after the break for the Geophysics and Hydrology in High-Latitude and High-Altitude environments part of the session. So I should quickly just introduce the Chevron Award, because the first three talks are candidates for this award. This is an award for a CGU award for the best student paper in seismology. And in addition to a slightly longer talk than usual, these will be 20 minutes, including questions. And so in addition to a slightly longer talk, the candidates for this award are required to submit a five-page extended abstract of their research. So I have a stack of those in front of me, and they've been very interesting reading. So the other thing I want to remind you of is that after the talks are concluded at 4 p.m. Eastern, so 3 p.m. for those of us on Central Time, we have the union-wide annual general meeting for the CGU. And I'd encourage you to stay on for that. But yes, so our first talk is by Jeremy Gosselin of the University of Ottawa, co-authors Pascal Audet and Bill Fry, and it's titled Teleseismic Constraints on Plate Interface Heterogeneity in the Hikurangi Subduction Zone, New Zealand. So, Mr. Gosselin, if you're ready.
All right, thank you for the introduction, Andrew. Just gonna. All right, so yeah, even though this is the Canadian Geophysical Union, we're gonna take a trip across the Pacific and talk about the Hikurangi Subduction Zone in New Zealand. And so yeah, I'm a PhD student at the University of Ottawa, supervised by Pascal Audet, and this works in collaboration with colleagues from the Geological Survey of New Zealand, GNS Science, that's Bill Fry, and Emily Warren-Smith. So the Hikurangi Subduction Zone is the transpressive convergent boundary between the Pacific and the Australian tectonic plates. So this is right here along the east coast of the North Island of New Zealand. And some things of note is that the oceanic lithosphere of the Pacific plate here entering the margin is on the order of 2 to 3 times the thickness of typical oceanic lithosphere. And this thickness actually increases further south of this Chatham Rise, and that's what's resisting subduction beneath New Zealand further south of Hikurangi here. And also of note is some studies on the level of plate coupling of the plate interface, or the megathrust fault, based on observations from GPS data from sites over the forearc here in Hikurangi. And these results suggest that there's a very sharp and stark contrast in the level of coupling of the plate interface along the margin. So what these colors mean is this red region here is basically where the plate interface is coupled. So the two plates are locked together, accumulating elastic strain. And so that's where you can expect a large megathrust earthquake and associated tsunami and other hazards. In contrast, the blue region is where the plate interface, so the boundary between these two tectonic plates, is uncoupled. So the two plates are just sliding past each other and accumulating no elastic strain. And so you don't expect a large megathrust earthquake in those regions. And atypical of subduction zones, other subduction zones around the world, there's a very sharp contrast in this degree of coupling along the margin, so from south to north here. And obviously this has implications for megathrust seismicity, but also seismicity and deformation and tectonics in general, and associated hazards. And so what we'd like to do with this study is look at passive seismic data recorded on the National Seismograph Network of New Zealand at all these stations over the forearc of New Zealand, and try to constrain structure, tectonic structure beneath these stations, and try to say something about the deformation and possible mechanical controls on plate coupling along the margin, so from south to north, and see if we can say something to help describe this phenomenon. So the type of passive seismic data we're looking at is called receiver functions. So if you're not familiar with this, I'll just give a brief overview. So this is looking at teleseismic recordings. So this is recordings of distant earthquakes. So you can imagine a large, deep, distant earthquake occurring on the other side of the planet. It will release a P wave that will travel through the deep earth and arrive nearly vertically beneath our three-component seismograph station. So this is on New Zealand. And it will arrive, as we can assume, a planar P wavefront. And that planar P wavefront will interact with all the structure beneath the station and produce converted and reflected and refracted phases that are diagnostic of the structure. And we can use that to infer the structure beneath the station. So a very simplified example, imagine we have this planar P wavefront arriving almost vertically beneath this seismometer that has a crust mantle boundary, so velocity contrast at 35 kilometers depth. Some of that P wave energy will be converted into an S wave that's polarized in the direction of the earthquake, so in the radial orientation. And so no associated energy orthogonal to that, so no energy in a transverse direction. But that S wave, that converted S wave, travels slightly slower than the direct P wave, so it will arrive at a slight delay time relative to the P wave. And similarly, we have these other phases that will reflect and refract off the free surface, and will arrive at accordingly longer delay times due to the greater travel path. And so we get this pattern of phases and we call this the receiver function, and it's diagnostic of this structure. And so we can use this pattern of phases to constrain this simple structure. And this is a super simplified example where the interface is perfectly horizontal and all the structure is isotropic. And so in this case, it doesn't matter if we're looking at an earthquake to the north or to the south, east or west, it will produce the same receiver function. But in the presence of anisotropy, or if this interface was dipping, that wouldn't necessarily be the case. So here's a couple of examples. And so we're plotting all of these receiver functions. These are just results from a recent study that's looking at this phenomenon. These receiver functions are plotted according to back azimuth. So whether the earthquake was to the north of the station, south, and so forth. And in the presence of horizontal azimuthal anisotropy, some of that planar P wavefront energy actually gets refracted into the transverse component. And so we end up with these phases on the orthogonal direction. But the amplitude and polarity of these phases actually depends on the orientation of the earthquake relative to the orientation of the structure, so the orientation of this anisotropy. And we see that as we go from north to south and back to north again, there's two cycles in these polarity changes according to the direction of the earthquake. And in the presence of plunging anisotropy or dipping structure, we also see these phases occur on the transverse component, but in this case, it's just a single cycle over back azimuth. So a signal that has a 360-degree periodicity in this case. So if we look at some actual receiver function data processed from the stations in New Zealand, here's an example from a station WPHZ. What we've done here is sort the data according to back azimuth. So 0 degrees represents north and 180 degrees south. And so the data are just sorted according to back azimuth. And we can see that there's all these phases within the receiver function data set that actually show a polarity reversal with respect to back azimuth. And of note, here I've just plotted this black dotted line, which represents an estimate of the delay time that would be associated with the plate interface. So that would be based on just a rough contour model of how deep we believe the plate interface to be beneath these stations. So any of the phases that are at earlier delay times or above this black line represent structure that's in the overriding Australian plate or overriding crust. And so these results, these observations suggest that there's anisotropy or dipping structure within the overriding plate. And just a couple more examples. Here's another station, MRHZ, and again, above the black dotted line, so within the overriding plate, we see these early phases that show a change in polarity with respect to back azimuth. And lastly, another station, HATZ, and again, above the black dotted line, so above the plate interface within the overriding plate, we see these phases that change in polarity with respect to back azimuth. So for all the stations over, I won't go through these 53 stations, but for all these stations, we observe these phases associated at depths associated with the overriding plate, indicating the presence of anisotropy or dipping structure. One approach to considering this type of data set would be to create a model that incorporates dipping structure or anisotropy and try to simulate waveforms and match our observed receiver functions. But we're taking a more heuristic approach in this case, where we take our receiver function data set and we just decompose it into a set of harmonics with respect to back azimuth. So imagine for a given station, you have n receiver functions. So you have your n radial and your n transverse receiver functions. And we're trying to transform the data set into a set of 5 harmonics. And what these harmonic components represent depends on this transformation matrix. So the first harmonic component is just the sum of all the radial receiver functions. So neglecting all of that energy that comes into the transverse component. And so that just represents the isotropic structure beneath the station. If we look at the B components, they're described by cos and sine terms as a function of back azimuth phi, and they describe structure within the data set that shows a periodicity of 360 degrees. And like we talked about, that's due to either dipping structure or plunging anisotropy. And likewise, the C components are cos and sine terms that show 180-degree periodicity. But rather than describe back azimuth relative to north, so relative to 0 degrees, we can try to solve for a parameter alpha that rotates our data set to be aligned with the dominant structure within the data set and basically maximize one of these harmonic components. So solving for alpha, we can actually solve for what would be the strike of dipping interfaces or the trend of plunging anisotropy. So what we've done for all of the stations is we've computed our receiver functions, computed our harmonic decomposition, and solve for this alpha parameter. So this represents the strike of dipping structure or the trend of plunging anisotropy beneath each of the individual stations over the Hickarangi forearc. And we perform this analysis only at a time window associated with structure above that black dotted line I showed earlier. So only structure within the overriding plate. And we can see there's a nice coherent pattern, but let's note that from north to south, in the south here, the orientation is very margin parallel. And we see this general rotation towards a more east-west orientation direction in northern Hickarangi. And not only can we plot the orientations, but we can also plot the magnitude or the strength of this signal. And we also see a change in the strength of this signal north to south along the margin. And I'll talk a little bit about that later. So from this analysis alone, we don't necessarily know if the structure is due to anisotropy or if it's due to dipping structure. And so one sort of comparison that gives us some confidence here is that some recent results looking at local shear wave splitting, so looking at S phases derived from local earthquakes within the overriding Australian plate. Identify anisotropy directions that are in good agreement with the sort of orientations we obtained from the receiver function. So closer to the coast here, sort of margin parallel, and in northern Hikurangi, this sort of rotation to a more east-west direction. But we can't exclude the effect of physical structures, so possible velocity contrasts or faulting within the forearc, because the Hikurangi forearc is actually heavily deformed. And in particular, there's this belt of dextral faults that runs the entire margin, as well as this other belt that runs predominantly through southern Hikurangi. And recent active source seismic identifies that although at the surface these faults are vertical, they actually splay, or they're believed to splay and interact with the plate interface at depth. So within the overriding crust, it's reasonable to assume that these structures represent dipping structures, and they could represent the manifestation of what we're observing from this receiver function harmonic orientation. But it's worth noting that in northern Hikurangi, our orientations obtained from the receiver function analysis don't agree with the strike orientations of these active faults. So one possible explanation for this change in orientation requires us to look at the back arc as well. So looking at all these active faults within the back arc of Hikurangi, this is actually the Taupo volcanic zone, TVZ. And this is actually an active spreading center. And it's causing, based on GPS data, it's causing this entire region to be under extension and rotation. And so a possible explanation for this rotation of the alignment of our receiver function observations could be that they either represent past physical structures within the forearc that have subsequently been rotated, or they simply represent a rotation in the direction of maximum horizontal compressive stress in northern Hikurangi. If we look at the magnitude of those harmonic signals along this transect A to B, that's what I'm plotting here in this figure. And compare that to the inferred level of plate coupling along the same transect from the GPS data that I showed at the beginning of the talk. So in southern Hikurangi here, close to A, we see that high plate coupling, so the plate interface is locked. In northern Hikurangi, it's uncoupled, so the two plates are sliding next to each other. And where this sharp change occurs correlates well with the observed change and drop in the magnitude of this harmonic signal, as well as the change in the direction of these harmonic signals. So it's telling us that southern Hikurangi versus northern Hikurangi, there's likely two totally different mechanisms for deformation and two totally different mechanisms that are manifesting these observed phases in the receiver function data set. So just to summarize, we calculate receiver functions at 53 long-running 3-component stations over the Hikurangi forearc, and we observe these phases at early arrival times at depths associated with the overriding plate, and they show this change in polarity as a function of back azimuth, so where the earthquake occurred. So this indicates the presence of dipping structure or anisotropy, and so we perform our harmonic decomposition to try to figure out the orientation of the structure within the overriding plate. We see this coherent pattern, but changes in magnitude and orientation that suggest totally different changes in the mechanism of deformation with north to south along the margin. And with that, I'll happily take questions. Thank you.
Thanks, Jeremy, for the great presentation. And So for the audience, if you have a question for Jeremy, you can type directly in the Q&A box, or if you want to speak directly to him, just ask Aziz to unmute you. Right, that's exactly what Az just typed in the chat box. Well, maybe while we're waiting for people to type up their questions, I have a question, Jeremy. In terms of the maximum compressional stress orientation that you mentioned as a possible explanation for the changes in the orientations that from your anisotropy results. I wonder if there are stress inversion studies in this area, like using Foucault mechanism solutions, try to see if there is indeed this kind of stress rotation, at least from earthquakes in the far crust.
Yes.
Oh wow. Okay. You didn't plan this question.
So yeah, this is probably the most recent results that looked at the entire margin. This is from Town and Dale from 2012. The only issue is that each of these orientations is like a cluster of earthquakes, right? And
right, yeah,
you're inverting for the stress orientation based on a cluster of earthquakes, but all of those clusters actually included overriding plate earthquakes and earthquakes within the downgoing slab. So it's actually difficult to resolve and like compare the two necessarily. And so it's unclear what these orientations represent, if they're above the plate interface or if those orientations represent horizontal stress within the downgoing slab.
Okay, I see. Yeah.
But yeah, this is probably the most recent study that looked at that. But yeah, that's an excellent question. So trying to discriminate overriding earthquakes from downgoing plate earthquakes and do the same analysis would be very useful.
Right, yeah, exactly. I think have a depth resolution would be the first thing to, yeah. Thanks, Jeremy. Wait, where's my Q&A box? I don't see anything in the Q&A, and as just sent a note that it's time to switch over to the next speaker. So let's thank Jeremy again, and we can switch for Paulina's talk now. Thanks.
Thank you.
Andrew, do you want to do the, yeah, thanks.
Yeah, okay. So our next speaker is Paulina Wozniakowska from the University of Calgary, co-authored by David Eaton, and the talk title is Identification of Regional Structural Corridors in the Montney Play Using Geophysical Data and Terrain Surface Analysis. So please proceed.
Hello, everyone. Thank you for the introduction. So the title of my talk is Identification of Regional Structural Corridors in a Montney Play Using Geophysical Data and Terrain Surface Analysis. I'm a PhD candidate in geophysics at the University of Calgary. So the outline of my talk, first I will touch base on induced seismicity and its relationship with the fault structures. And then I will explain the results of our geophysical data interpretation, which consisted on several steps. And finally, I will sum up with some conclusions. So in terms of induced seismicity in Western Canada, it tends to be strongly localized with the hydraulic fracturing wells. And here on the map on the left, I'm showing the main clusters of the induced seismicity above magnitude 1.5. So we can see that it concentrates in different areas. However, in terms of Montney hydraulic fracturing induced seismicity, it's concentrating only within the British Columbia province, which is pretty characteristic for this region. And also I want to indicate that unconventional development in Montney, it occurs within the whole formation. However, only induced seismicity from the Montney is visible in British Columbia province. Also, I wanted to indicate that indeed, the number of induced earthquakes skyrocketed since 2011, which corresponds to the increase in number of hydraulic fracturing wells from the Montney. The rest of the clusters that we can see in this map correlates, for example, with the corresponds to the on development, for example, of the Duvernay Formation or saltwater disposal or enhanced oil recovery. So it's currently established that induced seismicity risk, it's strictly related to the pre-existing faults that can be reactivated during hydraulic fracturing or saltwater disposal. So we know that we need to obtain better information about those fault distribution in the subsurface in order to manage this risk of induced seismicity. So we started doing the research, and it was published last year, which focused on the induced seismicity concentration in mountain formation. So here we were looking in these clusters of induced seismicity within mountain, and we used the machine learning algorithm to analyze different geological characteristics that can influence the occurrence of induced seismicity only within this part of the mountain formation. So we took this number of different parameters, and what we were calculating first, the probabilities that some specific hydraulic fracturing wells could be associated with induced seismicity. And also we estimated the feature importance, it's called. So it just indicates the importance of different factors in estimation of our results of the model. So one surprising thing was that we noticed that the distance of the fault, so influence of the faults, was indicated as least important. And here we conclude that just this database of faults that we provided to the algorithm was not entirely correct. And that's another reason like why we would need to improve this information about the faults. So the study area concentrates within the mountain formation extent. So the most clear feature in this area is the Dawson Creek Graben complex, which is a system of normal faults, which was formed in late Carboniferous, and as a result of the collapse of the Peace River Arch. Also, we have one element, which is Peace River embayment, which was formed in between Permian and Triassic. And finally, we have some structures corresponding to the Rocky Mountain Thrust and Fault Belt, which was formed between late Cretaceous and Paleocene. So in terms of those fault compilations, there are many of them. However, they are not clearly described and they are very ambiguous. So here I'm just showing that on the map on the left, where I compiled different fault compilations together to visualize how unclear they are. So we have multiple faults that corresponds to the same structure, for example, because many authors were just interpreting those data differently, or there are some digitization errors. So as a result, we have lots of faults compilations which are not clear. So it can be seen, for example, for the Gordondale fault, which as I outlined, or Hines River Creek Graben. So hopefully we have some seismic data which is crossing some of those structures, and we use those to try to find a way to better describe this faults in the subsurface in this region. I will just briefly mention about the potential data, because we also took a look into that in this area. So here I'm showing the residual total field as well as its isostatic residual gravity. And one thing that we can notice are those magnetic domains that appear east of the Cordilleran Thrust and Fault Belt. So we have those main magnetic domains here. And also there are some expressions also of the faults that are appearing on this anomaly map, which is High River Fault, Dunvegan Fault, and Tangent Fault. However, those are not all the faults that are in that area. So we see that there is no clear correlation between the magnetic anomalies and fault structures. Only in some cases that they tend to overlap. In terms of the isostatic residual gravity, we could try to see some curved linear features that could correspond to those fault structures. However, again, like this is not a clear expression. So I would say that those potential field data was not very helpful in trying to resolve those local structures, but we still investigated that to understand what they represent. So the workflow that we've used was three steps. And the first step was to perform the trend surface analysis based on the available well top data. So the idea was to calculate the residual of the trend surface that was produced for each of the formations. We have analyzed several formations, which I'll describe later. And the next step, after we had those residual maps of the residuals, we performed this seismic interpretation to identify the structural features or the groups of faults that are within the area of the study. So I'm just showing here one example of the seismic line that we used. And the final step was just to put it all together and perform the structural interpretation, which is the combination of this trend surface analysis and seismic interpretation, which gives an overview on the more regional image of the structures in that area. So trend surface analysis is the geostatistical, is the method that uses geostatistical analysis. It was originally published in 2009 by May. And here the author was producing those residual maps based on the formation tops. As I mentioned, that's the idea. And the lineaments and faults are interpreted in the locations where we have the sudden changes in these residuals, which corresponds to this potential line fault structures. So I was trying to reproduce this methodology, and this is the main workflow of TSA. So first we have our formation tops, and those are the formations that I decided to use for this study. So we are having nice view across the geological time scale, and to understand like temporal development of those structures. So based on those formation tops, we are calculating the regional trend surface using local polynomial regression. So to create a surface which presents the regional trends of the formation without some local lineaments and local structures. So once we have this regional surface, we can calculate the residuals, which is basically the difference between what was interpolated as a regional trend surface and the formation tops that were picked by the geologist. So those are our residuals, which indicate some small changes or linear patterns in terms of for some of those structural features. So once we have those residuals, we can interpolate those to create those maps of the residual maps, which are helps us to express those structural trends. And finally, those residuals are validated with the regional seismic data that is available in this study. So I'm just showing here those residual maps for all the formation that I mentioned before. And for example, we can see on some of them some special features. For example, for the Cretaceous, we could see the foreland structural fabric, which indicates that there is a lot of going on, and there are many smaller linear features or continuous fault features in that part. For example, we have another structure here, which is based on the literature. It's around the Monaias field. So this was also appearing on these maps. Of course, we have Dawson Creek Graben Complex, which is the most clearly expressed on the Dibolt Formation, as well as we have some Leduc reefs, which are shown on the Devonian. Also, they are appearing on some other residuals. So this is just the main idea, what we can get from those residual maps. And here I wanted to introduce the idea of the structural corridors. And so the idea is that the geometry of those fault structure is not simple. Those are not singular faults, but we can see that they tend to appear in more groups as a group of faults. So we decided to try to pick those structures as a structural corridors. So that's how for example, how those corridors looked on our lithoprobe lines that we've identified, and also some literature examples here. So in terms of seismic data that we've used, we were using the lithoprobe seismic line, which is part of the Peace River Arch industry seismic experiment, and we were using lines 11 to 13, as well as some seismic line that was provided by Pulse Seismic. And we can see that within this lithoprobe profiles, we had multiple faults that were identified in the past, interpreted in the past as kind of structural corridor features. Like we can see that they are grouped, they are not single features. So that's that's what we were using for this part. So in total, we identified over 20 structural corridors using this approach. So basically, we were identifying the relationship between the length and width of those structures using our data, seismic data, wherever we had those available. So we were able to calculate those widths. And then we were finding that relationship with the geometry. So basically with the length of the corridors. So once we've estimated those relationships, we could try to expand that to those areas there where we do not have the seismic data. So that's how the width of those corridors outside of seismic information was obtained. So those structural corridors reflect some structural deformations, specifically the formation of Dawson Creek Graben complex due to the collapse of the Peace River Arch in late Carboniferous, as well as some development of those Cordilleran thrust fault belts and the structures east of that that was formed in late Cretaceous and Paleocene. And sometimes it was not visible. So I'm showing here the DeVault residual. Some corridors were not clearly expressed on the DeVault formation residual, but I was able to identify some structures, for example, from basal fish scale zone. So they are outlined in lighter colors here. We could also identify some of the horse and graben structures, and that's it. I just labeled that according to the literature example, so we could see how nicely this overlaps, and it gives us an idea of how this Dawson Creek Graben complex looks like. So just to conclude, because I think I'm about to end, the current fault databases are very ambiguous and uncertain. So we have very commonly some errors from digitization. There are some old compilations, or many authors are using different nomenclature. And also the Dawson Creek itself is very complex. So it's very useful to see this regional trends and from more regional perspective, and trying to understand those structural corridors type of structures wherever we were able to get intersection with the seismic data, and then expand that to other areas. So in total, seismic interpretation that was complemented by this trend surface analysis allowed us to map over 20 kilometer regional structural corridors within northeastern BC and northwest Alberta. And with that, I would like to acknowledge Geological Survey Canada, as well as the sponsors of Microseismic Industry Consortium for sponsoring this research. And I will be happy to take any questions. Thank you.
Thanks, Paulina. Great talk. Again, from the audience, if you have a question, feel free to type in the Q&A box or unmute yourself to ask directly. Well, I feel like since my audio is already on, I will just go ahead and ask my question. Sorry for kind of take advantage of this opportunity. So I wonder, for the Dawson Creek area, or the area between Dawson Creek and Fort St. John, there has been a very rich seismicity catalog for the past 3 and 4 years. I wonder if you try to kind of correlate the seismicity with these regional structures that are being identified from your TSA and the corridor sort of categorization, and see if those events were more locally related to, for example, hydraulic fracturing, or more representing the active regional fault displacement. Or
Yes, so we were starting looking into that, and honestly, I have it like as a hidden slide in case someone asked about that. So maybe let me just I could try to show that, because it was not in the expanded abstract, so I wasn't sure if I should show that, but I overlapped those structural corridors. We have our own like high quality seismicity catalog, so I decided to use that one. Let me just unhide. Okay, so those gray events correspond to this induced seismicity, and we have those seismic lines, and we can see that most of those induced seismicity corresponds or is confined within structural corridors that we outlined. We have some seismic clusters that are outside, and we are interpreting those as a potentially either like we just simply don't have data for structural interpretation in that part, or basically those are strike slip structures that are not visible, like they don't have vertical displacement, so we cannot see that. But in general, like for those are the very beginning like conclusions that I have from that. But my guess is just maybe we are not even able to see those. But most of those events that were located, I would say majority of that it's confined within the structural corridors. So I'm not sure if that answers your question.
Yes, it does. Thanks a lot. It's great to see that correlation there. Yeah. Well, if there are no other presentation.
Thank you very much.
So, so the final presentation in this series of talks for the Chevron Award is by Tracey Kyryliuk of the University of Ottawa, with co-authors Pascal Audet, Jeremy Gosselin, and Andrew Schaefer, and it's entitled Tectonic Fabric Along the Queen Charlotte Margin from Receiver Function Analysis. So over to you.
Hi, so I'm Taylor. I'm a master's student at the University of Ottawa, and today I am presenting my research together with Pascal Audet, Jeremy Gosselin, and Andrew Schaefer on the tectonic fabric along the Queen Charlotte margin from receiver function analysis. Oh, my annotation. There, okay. So to begin, we'll just take a look at our study area. So this is just it on the greater map here, and we're looking around this group of islands known as Haida-Gwaii off the coast of British Columbia. So over here we have the Pacific plate with this motion relative to the North American plate and the North American plate here. And on the coast of the islands of Haida-Gwaii is the Queen Charlotte Fault. And it is a transform fault, and it's the plate boundary between the Pacific plate and the North American plate. And so we're looking around not only at the islands, but in the greater area as well. And historically, this area has undergone a few different tectonic regimes. So it underwent subduction, which led to the formation of a magmatic arc. And then later on, it went through a series of transpression, first translating slivers of coastal material or continental material known as terrains, translating them down southward and then back upwards. And so we have this accretion of different terrains as well as shear zones and exposed batholiths from that magmatic arc. And so our motivation for why we're looking into this area is that there's some amount of convergence between the Pacific plate and in the North American plate. And so there have been a few different models suggested for how that convergence is accommodated for. So one model is that it's purely strike slip, and it's just accommodated with crustal thickening. Another model is that it's a strike slip margin, but there's a portion of the plate that's detached and under thrusting orthogonally to the margin. And a third model is that the Pacific plate is obliquely subducting beneath North America. So in 2012, there was a magnitude 7.8 earthquake off the coast of the islands, and it had a thrust mechanism, and it also generated a local tsunami. So this supports the subduction hypothesis. And the significance of subduction is that with subduction, you get the chance of having large earthquakes, so megathrust earthquakes, as well as damaging tsunamis. And so looking again at this map here, the proposed extents for how far the Pacific plate could be subducting beneath North America are somewhere in this green polygon. And so what we're going to do is analyze scattered wave fields from teleseismic body waves, method known as receiver functions, from all seismic stations in the region around Haida-Gwaii, and to look for evidence of dipping structures or anisotropy. So our data set composes of 73 3-component stations. They're just denoted here with these upside down triangles, and they're grouped by color by different regions. So we have Haida-Gwaii, Southern Alaska, and then Northern and Southern mainland British Columbia, as well as Northern Vancouver Island. And we're including more stations than previous studies using receiver functions trying to analyze the subduction here. So we're including stations on the mainland and not just on Haida-Gwaii. And then we're also incorporating new stations. So a lot of stations have been since deployed after this 2012 event, and they should have collected enough data now to produce some good results. I'm just going to quickly go over receiver functions again, although we had a previous presenter also cover them. So receiver functions rely on large distant earthquakes producing teleseismic waves that when they reach the seismometer, they can be approximated to a plane wave, and that initial P wave is also near vertical, and it will then interact with discontinuities beneath the receiver, producing different P to S conversions, and the timing and amplitude of those conversions can give us information about that subsurface structure. And here we're just seeing an example of a purely horizontal and isotropic medium. So this would be the radial component of the receiver function, but we also have another component which is perpendicular called the transverse component. And so here just shows an example of two receiver functions for a situation where we have an anisotropic layer and then a dipping layer, which are the two situations that we're interested in investigating. And we can see for both of these that on the transverse component, we have a signal present. So if it was just horizontal and isotropic, we wouldn't have anything on that transverse component. And so we're looking for something like this in the receiver functions that we're producing. And we're also taking it a step further and doing a harmonic decomposition. So we're decomposing the receiver functions into back azimuth harmonics. And we're specifically interested in the B components, which are represented by signals that have a 2π periodicity. So if you'll look again at the transverse components here, we can see that they go through one cycle over the 360 degrees. And what we'll then do is minimize one of the B components, and the angle that we can use to minimize this, or the angle we find that minimizes this, will tell us something either about the strike of a dipping interface or the trend of fast axis of anisotropy. So this is an example of our results for one of the stations on Haida-Gwaii. So this is station DIB. This here just shows the different phases we're using. So we have the P phases and the PP phases as well. And this is what the receiver function looks like. And so you can see if we're looking at the transverse component that we do have a 2π periodic signal. And so then we did a harmonic decomposition for this station. Just the bottom here shows the time. And for a time window of 1 to 2.25 seconds. So when we optimize it for that time, we've got an angle of 338 degrees. And we also, I'm just going to show the results from another station, which is interesting. So this station BNAB is lying within that polygon where the extents of the Pacific plate could reach. And again, we're seeing something on the transverse component. And we also see something later on here, around 7 to 8 seconds, between 200 and 300 about back azimuth. So this could potentially be a signal coming from the Pacific plate, but it needs further investigation. We're just focusing now on crustal depths from a time window of 1 to 5.25 seconds. And this is what the harmonic decomposition looks like for this station. And just to highlight that 1 to 2.25 seconds time window, we found an optimal angle of 152 degrees. And just to illustrate, this is what the different time windows that we're looking at are. And we did the harmonic decomposition for every station, for every time window, and then plotted these. So the length of the bars is just the strength of the signal. And this is our first time window, and then our second time window, which is 2 to 3.25, and then 3 to 4.25, and 4 to 5.25, so later and later time windows. These are kind of messy to look at, so we plotted them as Rose diagrams. The colors on here just correspond to those regional sets that I mentioned earlier. And so we see that we have this somewhat coherent orientation of these results here for this time window. And then if we look at this later time window, it's not as coherent, but somewhat. And we also have this almost perpendicular jump in comparison to the previous time window. But if we look at these later time windows, they kind of just lose coherence. So we're going to focus on analyzing the results from the 1 to 2.25 second time window. So we looked and found what the mean angle was, and it was 329 degrees. And just plotting this separately for each region. And when we looked at plate motions, the one that seemed to align the best was the Pacific plate motion relative to the hotspot. Even for stations on northern Vancouver Island, which is not above the Pacific plate at all. We also compared our results to other studies in the area using different methods. So these 4 studies looked at shear wave splitting analysis from SKS phases. And along the margin, the fast directions are margin parallel, but as we go on land, they start to trend east to west, and southward they become orthogonal to the margin. And in comparison with our results for that first time window, we are seeing also this margin parallel near the Queen Charlotte Fault, but on land, our results do not agree. Although when we look from our later time window of 2 to 3.25, we do start to see a more east to west trend developing. We also looked at surface wave tomography results. So these 2 time periods of 15 seconds to 20 seconds are both sensitive to crustal depths. That's just what this plot here is showing. So once again, we're seeing a northwest orientation near the margin. And for this, this time period here, which is sensitive to deeper depths, we're seeing as we go on land, we also start to have a more east to west orientation. We also compared the results to faults within 5 kilometers of our stations, but we found that they didn't really line up well with our results. However, when we looked at a more regional scale, they were much more northwest oriented. And this leads back to the history of the region. So the lineaments of this region are predominantly northwest oriented and a crustal scale, and the result of the translation of those terrains historically. And the foliation trajectories in the shear zones are also predominantly northwest oriented. And in some areas, we have this kind of swirling pattern that is attributed to the batholiths. So again, from the history of this region, And perhaps these random swirls can account for some of our orientations that don't line up with the rest in our data set for that 1 to 2.25 second time window. So in conclusion, or to discuss, our results seem to be coming from crustal depths because the SKS results were attributed to upper lithospheric mantle. So our results must be coming from something else. And on the mainland, it's possible that our results are from large-scale faults in the coastal shear zone, and they're consistent with those foliation trajectories. So maybe our results are anisotropy caused by that foliation, or perhaps it's caused by dipping structures on the mainland that formed from transpiration when we had those terrains being accreted. And when we're looking at Haida-Gwaii, perhaps our results are from dipping structures along the margin. So in conclusion, we looked at receiver functions for a wide selection of stations in Haida-Gwaii and the surrounding region in order to study the tectonic fabric. And when we performed the harmonic decomposition, we found that the receiver functions had a coherent orientation at crustal depths. And we attributed this to the result of the tectonic assembly on the mainland and a result of the plate motions along the margin. So next steps in this research would be to start using velocity models to convert our harmonics to depth, because right now we're just looking at time, but looking at depth would also be interesting and helpful. And also increasing the depth we're looking at. So investigating more around that 7 to 8 second signal. Another thing we can do is incorporate OBS data, because right now there's a large gap in coverage because so much of that area where we have that green polygon is underwater. And then also to start doing some forward modeling to see if we can come up with some models that work with our results. And this concludes my presentation. Thank you for listening, and let me know if you have any questions.
Thanks, Tracey. Please go ahead to ask your questions, either in the Q&A box or unmute your audio.
Perhaps if no one else has a question, I'll just jump in with a quick one. I guess I'm not sure I understand why specifically you're attributing the Haida-Gwaii results specifically to dipping structures rather than anisotropy. Why would it be different there than on the mainland?
I think because it doesn't have as much of the same history as on the mainland, and the plate motions are like active right now there as well. And the crust is also a lot thinner there too. Does that help answer? Okay,
If no other questions are forthcoming, maybe I can pop in with another one. I was sort of curious from the data, how would you go about determining, like, do you think you have enough information to separate out anisotropy from dipping features? I mean, if you bring in other data types?
maybe if we brought in other data types. But from the data itself, like some of them are like pretty messy, so it's hard. And it could also even be there's a combination of dipping and anisotropy. And I think that's part of the reason why we look at the harmonic decomposition, is to try and get some things out of this. So yeah, it's a combination of looking at that and looking at the receiver functions. And also, like if we do the forward modeling and try to create different scenarios. So some models with anisotropy or some with dipping, and see what the receiver functions from those look like and compare.
I don't see other questions in the Q&A box. So thanks, Tracey, again for the great talk. And Andrew, maybe you can wrap up the session, or the first part of the session. Thanks.
Thanks, Shaghayegh. So yeah, so thanks once again to the speakers for a trio of excellent talks. And I also just want to point out again that we made them do extra work for this, because the Chevron award also, the process also requires an extended abstract. Now I believe we're going on to a short break here, which at which point we'll turn over the chairing to Andrew Ireson from the University of Saskatchewan will be taking over. So I gather we're going on break until 2:30 Eastern time. So thank you very much, everyone, and I'll turn over the convening at this time.
Yeah, I'll see everybody back here in 5 minutes for the hydrology session. And as well, you can go ahead and play the video if you like while we wait. Okay, so hello everybody, and welcome back to this final session of the CGU 2021. And this is the hydrology session, of course. And so we're going to have 5 talks now, broadly themed around sort of land surface processes in frozen environments. So without any further ado, we'll move on now to our next speaker, who is Wang. From the University of Waterloo, who's going to be talking about, again, energy partitioning, and this is in the Rocky Mountains. So Yi, would you like to take over?
Yeah, thanks, Andrew. So hello everyone, my name is Yi. I'm from University of Waterloo Hydrometeorology Research Group. Today, I will be presenting our research on the relative importance of the biophysical and the meteorological effects on growing season surface available energy partitioning at high altitude weather in Canadian Rocky Mountains. And then just give a very brief context of this research. So the balance of the Earth's energy components, including the ground heat, sensible and latent heat, impacts the global climate systems and the hydrological cycles. And then the available surface energy is the total of the sensible heat and the latent heat. So this partition can be expressed by the bond ratio. And then this partition is not just a physical process, it's also affected by vegetation's morphology and the physiology traits. And then we can use the Pullman-Monteith approximation to model the partition. So in the Pullman-Monteith approximation, the RS, which is the surface resistance, is denoted as the biophysical control in our study, while the rest of the terms, such as the RI, which is the climatology resistance, RA, which is the aerodynamic resistance, and the ratio of the delta to gamma, which is kind of like an equation with the to the air temperature. They are grouped as the meteorological factors in affecting the bond ratio. So the right now, the mechanistic understanding of on how the biophysical factors and the meteorological factors affect the partitioning process are still lacking. And then we usually use the relative contribution methods, such as the linear regression methods, to quantify the relative contribution. But those methods usually have assumptions such as the linearity and the independence of the variables. These assumptions may not always hold true, and then this will cause a lot of the uncertainties in the relative contributions. And then moreover, the ground observations on the surface energy partitioning on high elevation ecosystems are insufficient. And then it's well known that these high elevation ecosystems are vulnerable to climate change. So our objective is to develop a more comprehensive methods to quantify relative contributions, which can take the indirect linkages between environmental variables into account. And then we would like to quantify the relative importance of biophysical and meteorological controls on the available energy partitioning in response to climate change by using these methods in our 3 representative high elevation wetland ecosystems in Kananaskis, Canada. So here is our study site. We have 3 sites. Sibyl Fen is our lowest elevation site, and then it's located at the foothill of the Canadian Rocky Mountain, and it's valley confined, surrounded by forest. The next site is Birstall Marsh. It's situated at the mid elevation of the Spray River Valley. And our highest elevational site is Bonsai Meadow. It's located beneath the head wall of Fortress Mountain. And then the table 1 just showed a summary of the climate conditions of each site during the growing season of 2018 to 2019. And then in each site, we have a eddy covariance tower operated continuously during the 2 growing seasons. So now let's look at our methods. We use the sensitivity analysis to quantify the effects of the explanatory variables on the response variables. So the sensitivity coefficient is calculated as the equation 1. And then the magnitude of this coefficient is the change in response variable as a result of 1 unit change in the explanatory variable. And then to account for the interactions, those indirect linkages among the environmental variables, we combine the Pullman-Monteith equation and an empirical model on the responses of the canopy conductance to vapor pressure deficit. The 2 models are widely used in the hydrological studies. And then by combining the 2 models, we draw a tree diagram to show how environmental variables are linked to each other, and then finally how they are linked to the bound ratio. So from this tree diagram, you can see that both the biophysical factor, which is denoted as the surface resistance, RS, and the rest of the terms, which is the meteorological factors, they are overall affected by the net radiation, the ground heat fluxes, the relative humidity, temperature, elevation, and wind speed. So in order to have a mechanics understanding of how climate change affect the surface available energy partitioning, and then to separate the biophysical and the meteorological controls on the bound ratio, we developed the 3 scenarios. So in each, the temperature scenario, the net radiation scenario, and the relative scenario, the relative humidity scenario. And then in each scenario, we only assume that 1 environmental variable change, and then the others are kept as constant. So so for example, in the temperature scenario, the biophysical control, the magnitude of the biophysical control is the changes in the bound ratio in responses to the changes in surface resistance that is caused by changes in the temperature, while the meteorological control is the differences between the overall changes in the bound ratio in responses to changes in temperature minus the changes in bound ratio under the biophysical control. So by doing this, we can separate the biophysical and meteorological control in our study. So now let's look at the result part. So first, I'd like to show the daytime half-hourly average bound ratio of the 3 sites across the 2 growing seasons. So we can see that the bound ratio have the similar magnitude across the 3 sites, and then also across the 2 years. And then it's generally the latent heat is 2 times larger than the sensible heat, despite that those weather ecosystems belongs to different type and have different geographical settings. And then we look at the relative controls of biophysical and the meteorological effects on bound ratio in response to climate change. And then we found that in any scenario, the meteorological control, which is indicated by the dark gray box, the absolute magnitude is greater than the biophysical control. So that means that the meteorological factor is more important than the biophysical factors in the surface energy partitioning in all these scenarios. But in terms of how they increase or decrease the bound ratio, they differed with different scenarios. And then since the meteorological control is more important, then we look at which climate variables are the most important one in regulating the surface energy partitioning. And we found that the bound ratio is most sensitive to temperature than to the net radiation. And then increasing temperature tend to decrease the bound ratio, while increasing the net radiation tend to increase bound ratio. So our preliminary results show that the surface available energy partitioning is more influenced by the meteorological control in our 3 high elevation wetland ecosystems. And then the other key messages from our study is that the high sensitivity of the available energy partitioning to temperature suggests that the energy balance and the water and the carbon process may be significantly impacted by the warming in the high elevation wetland ecosystems. And then in the last slide, I would like to thank our canastic teams for field work, and then the organizations for supporting our research. And then I would also like to thank everyone for attending my presentation. And I'm happy to take any questions. Thank you.
Ooh, sorry, thank you very much, Yi. That was very good.
Thank you.
Please, if you have any questions, put them in the Q&A. And while we wait, I will just ask a very general question. How do you think that the sensitivity analysis is practically useful for us?
I think it's very useful. How to say? So first of all, I think it's mathematically robust analysis, but it's subject to the structure of the model. So, for example, in our study, we used the permanent teeth and the orange canopy conductance model. So maybe the sensitivity analyzed our result is subject to this model structure, but since they are widely used, and then they are generally suitable for a variety of the ecosystems, we can use them to understand different environmental variables affect how they affect our response variable, and then we can use the result to improve our model structures, and then if we have improved model, and then we have the site measurement, and then we can kind of compare to see if our calibration or any improvement can really improve the representations of the models in representing the actual site situation.
I see. Yeah, so but basically what you're saying is that you can improve your models, but through the sensitivity analysis somehow.
Yeah.
Okay. Okay, well, thank you. Any other questions for Yi? Doesn't look like it. So with that, thank you very much, Yi, and we'll move on to our next speaker now. And that is Evan Wilcox from Wilfrid Laurier University, who's going to be talking about snowmelt in the Northwest Territories. So Evan, if you'd like to take it away.
Okay, I think you can all see this now.
Yes.
Okay. All right, hi everybody. So today I'll be talking to you about how freshet recharge occurs in thermokarst lakes between Nunavut and Tuktoyaktuk using stable water isotope sampling. So a bit of a background about our study area here. We're in the Mackenzie Delta uplands, which are kind of north of Nunavut in the far northwestern corner of the Northwest Territories. It's home to the Nuvialuit and the Gwich'in people. It's underlain by continuous permafrost, so anywhere where you don't see a lake, the ground has got permafrost under it, and of course an active layer above that permafrost, which thaws in the summer and refreezes again in the winter. There's about 15,000 lakes in this region, most of which were formed through thermokarst processes thousands of years ago. So permafrost with lots of ice in it thawed and created depressions, and lakes formed in those depressions. They're only about 1 to 5 meters deep on average, and they're quite small on average, only about 18 hectares. You can barely see most of the lakes actually from this far zoomed out. And it's quite cold here. Average air temperature is -9, with snowmelt occurring in mid to late May most of the time now. And most of the region you see here is just shrub tundra. There's a few forest stands in the southern third there, but all of the lakes that we looked at were covered by shrubs or shrub-free tundra. And there's about 250 millimeters of precipitation annually in this region, and about 150 millimeters of that is snowfall. So we're interested in snow and snowmelt runoff because it represents a large water source of water for lakes in this region. And a process I'll just give a bit of background to because it's important to understanding all the results, is a process called snowmelt bypass. So here we have a theoretical cross-section of a lake at the time of snowmelt runoff or freshet runoff. So we have lake ice on top of the lake, and we have our freshet runoff flowing in at the edges of the lakes. And that freshet runoff is just freshly melted snow flowing over top of a frozen soil layer, so it's at 0 degrees roughly. That's flowing into the lake right under the ice, which is also 0 degrees. And of course, the interesting property of water is that from 4 degrees to 0 degrees, water gets less dense. So we have less dense 0 degree water right underneath the ice, and then we have denser water as we go deeper in the water column. And that leads to the freshet runoff not really mixing with a lot of the lake water under the ice because it's less dense than the deeper water. So it tends to just flow right under the ice and out of the lake without really mixing with a lot of the water underneath the ice. At the same time, we have lake ice that's stopping any wind going across the lake from mixing that freshet water with the pre-snowmelt lake water either. So this process has been observed a lot in all sorts of ice-covered lakes around the world, from what I gather, but not much is known about how it varies from lake to lake. So that kind of set up our research questions we had, which were how much lake water is replaced by freshet runoff in spring, knowing that, one, snow makes up the majority of precipitation in the region, but at the same time, we have this snowmelt bypass process going on. Two, what affects the amount of lake water replaced by freshet runoff? So were there some lakes which were having more of the water replaced by freshet runoff and less, vice versa? Are there any watershed or lake characteristics which we could tie to those? And three, what are the sources of water that contribute to lake water replacement? So is it all just snowmelt runoff? Is there some soil water mixed in there? We weren't quite sure. So to answer these questions, we relied on stable water isotope sampling, so deuterium and oxygen-18. And these are very useful isotopes for us because we can use them to differentiate between different sources of water, mostly rainfall versus snowfall in this region. And we can also use the change in isotope composition of a lake to calculate how much of that lake water has been replaced by a source of water. So we set out on our snowmobiles and we sampled 17 lakes between Nunavik and Tuktoyaktuk before the snowmelt occurred. We just drilled through the lake ice with an auger and took a water sample. We did have to correct for fractionation from the water into the lake ice because the heavy isotopes tend to go into the ice. I won't show that here, but we were able to correct for it quite accurately, it seemed. And then we went after the snowmelt had occurred and the lakes had become ice-free, and we took water samples again just from the edge of the lake, accessing them via the highway. So how do we calculate the amount of lake water that's been replaced just using isotopes? So on this graph on the right, you may not be familiar with, we have our oxygen 18 isotope on the x-axis and the hydrogen or the deuterium isotope on the y-axis. We don't need to worry so much about the numbers. We're just going to be looking at relative changes in these two isotopes as they pertain to the lake samples. So in order to calculate the amount of water in a lake that's been replaced, we just take the amount of lake water that was there before snowmelt and look at how far the isotope composition has changed after snowmelt. So that's a very simple equation, and we're essentially just taking this change, which is the change between pre-snowmelt and post-snowmelt, and dividing it by the distance between pre-snowmelt and the source water. So we assume that if the lake after snowmelt is the same as the source water, that all of that lake water has been replaced by that water source. So now to back up a bit, how do we calculate what the average water source of a lake is? So we call this delta I. And first we have to calculate and measure a few things about the isotope sort of framework in this region. First, we calculate a point called delta star, which is the isotope composition of a lake as it desiccates, or the last drop of water before it's fully evaporated. And for isotopes, this point is controlled by the relative humidity and the air temperature of the region when it's ice-free. So we use an equation to calculate that, and we know that all lakes are going to trend towards this point as they evaporate. And the closer a lake gets to this point, the more evaporated it is. We also have the local meteoric water line, which is this black line here, and all the precipitation in the region is going to fall pretty closely along that line. So snow is going to be further down the line, rainfall is going to be further up the line, and then the average of those two, which we call delta P, is halfway in between. So we use those as our references. So then if we want to know the average water source in a lake, all we have to do is extrapolate from delta star through the isotope composition of that lake in this plot until it intersects with the local meteoric water line. So here we're getting a water source that's pretty close to that of rain. So that's how we use delta I in the previous slide I showed about how we're calculating the amount of lake water that's replaced. But it's also useful to calculate delta I because it tells us, is the water source more like rain or is it more like snow? And we can tell where that water came from. And we're going to use, we calculated this before snowmelt and after snowmelt just to see how the water source shifted after the snow had flowed or the snowmelt had occurred. Of course, we assume that the water source was probably going to be like snow. So first, we'll just look at how the isotope composition of the lakes changed before and after the snowmelt occurred. So here, just to give you a reference of these 17 lakes are now plotted on the graph on the right-hand side. And just draw your attention to the legend here. So the teal turquoise squares are the lake isotope composition before snowmelt. And the lime green is the lake composition post-snowmelt. I'll just point out a number of different trends we can observe from this and what they mean. So the first thing we see is those lime green points, post-snowmelt points, are shifting towards delta P, which makes sense. The lakes have just received, snowmelt runoff inflow, and we sampled them right after they became ice-free, so there wasn't any chance for any evaporation to occur, really. So that made sense. But there wasn't so much of a change in the isotope composition, considering that snow represents 2/3 of all the runoff, or all of the precipitation in this region. It was a bit surprising that there's still quite a lot of overlap pre and post snowmelt. The next, and that again, just the same thing, is that a lot of the lakes still plotted along this line between delta P and delta star, which we call the evaporation line. So a lot of them still had an evaporated signal that indicated that not a lot of water had been replaced. And the last interesting thing is that a lot of these post-snowmelt points are plotting above delta star. And if you think back to how we calculate water source, if you're taking a line from delta star through one of these post-snowmelt points until the local meteoric water line, that is going to give you a source that is more rainfall-like than snowfall-like, which is a bit peculiar because we've sampled immediately before and right after all the snowmelt had just occurred. So that was strange to see, but we'll explain that here in a minute. So the second big question we had is how much lake water is replaced by freshet runoff? And the median was about 23–24% of the lake's volume was replaced by freshet runoff, but we had quite a spread going up to nearly half of a lake's volume being replaced down to only 5% of a lake's volume being replaced. So that was a pretty big spread. And we wanted to know if there's anything that explained this variation. So what affects the amount of lake water that's replaced by freshet runoff? And there was a really strong relationship with lake depth. So on the y-axis here, we have the amount of lake volume replaced by runoff. And on the x-axis, we have lake depth. And you can see that as the lake gets deeper, less of its water tended to be replaced by runoff. And that slope is about 13% per meter of lake depth. So if a lake is 3 meters versus 2 meters, there's 13% less replacement of the lake water in the deeper lake. So that was just a simple test of all the different relationships between lake and watershed characteristics we had. An interesting one is I kind of expected that if a lake had a larger watershed and therefore more snow in it and therefore more snowmelt runoff, that maybe you would get more of that lake volume being replaced by freshet runoff. But that didn't turn out to be the case. And that's probably because of snowmelt bypass. And you can just picture a kind of conveyor belt of snowmelt runoff flowing underneath the lake. And it doesn't matter if there's more snowmelt runoff going into the lake, it just isn't able to mix with the lake and change the isotope composition of that lake. So why do deeper lakes have less snowmelt runoff replacement than shallower lakes? We expect that it's in a deeper lake, that layer of sort of mixed freshet runoff with lake water underneath the ice, that layer thickness doesn't seem to change very much. And that in a deeper lake, you're going to have a larger volume of the lake isolated from mixing with the runoff that's coming into the lake. So you end up with this same thickness of layer of freshet runoff under the ice, but in a deeper lake, it's likely that that's just a smaller relative volume of the lake than in a shallower lake. And that seems to explain why we get this strong relationship between lake depth and lake water replacement. So our last question that we had, which was, what are the sources of water that comprise freshet runoff? So here we just have delta I, or source water, plotted, and we have to offset them off the meteoric water line because they all are going to plot along that line, and then we can't really see what's going on. So we have pre-snowmelt is represented by the dot, and then the direction it's going in is represented by the arrow and where it got to post-snowmelt. And those are just offset perpendicular from the local meteoric water line for every lake. And you can see the blue lines are going towards rainfall and the red lines are going towards snowfall. And what you see for almost every lake except a couple is a convergence towards delta P, which is a mixture of snowfall and rainfall. And why would it do that when we've just had a big snowmelt runoff event? Like all of the snow for the whole year has just flowed into these lakes, we thought. Why wouldn't it trend towards snow? So it's likely that it's a mixture of soil water in the active layer and snowmelt runoff flowing into the lakes, and that the properties of snowmelt bypass just tend to favor active layer runoff going into the lakes. So we have more snow-sourced runoff at the beginning of the year, and that is just flushed out of the lake. And as the snowmelt runoff is occurring, it trends towards active layer-sourced water. And that's because the active layer is thawing, the snowpack's depleting, and probably by the end of the snowmelt season, the water going into the lake is able to mix with the lake water a bit more easily because as the lake warms up. See, I'm a bit over time there, sorry. So the two things we need to know is freshet runoff replaces lake runoff dependent on the lake depth, with deeper lakes experiencing less snowmelt replacement or freshet runoff replacement, and that we actually get a lot of active layer runoff left in the lakes because that's the water flowing into the lakes at the end of the snowmelt period. Thank you.
Great, thanks, Evan. Running a bit long there, but thank you. If there are any questions for Evan, we can have them quickly. Otherwise, based on time, I'm going to push on. Thank you very much, Evan. If we have time at the very end, we may come back to you.
Thanks.
And so we'll move on now to
Shay.
Shay, thank you, from the University of Waterloo. Take it away, Shay. Thank you.
Thank you. Sure. Okay. Hi again. My name is Shay. I'm PhD candidate of Water Resources Engineering, and today I'm going to present our recent in progress work paper, which is about developing a multinomial machine learning model for simulating land cover change in the discontinuous permafrost regions of Northwest Territories. So in this presentation, we will have 4 sections. Introduction, I will talk about our study site, the study site that is selected for this project, the methodology, and I will present our final results in this study. Our motivation, the main motivation of this study is about a recent data that was provided by NASA, which is telling 40% of the world permafrost is set to thaw by 2100. The rapid evolution of lowland discontinuous permafrost region in Northwest Territories is another motivation of this study. Permafrost thaw in discontinuous permafrost region is influencing permafrost distribution and extent, and it is intensifying the rate of fragmentation in permafrost plateaus in Northwest Canada. Due to local hydrological and ecological impacts of permafrost thaw and corresponding land cover changes in Northwest Territories, it is desirable to be able to calculate the rate of land cover transition, model pattern of transformation in each land cover, and predict evolution of the main land covers in Northwest Territories or discontinuous permafrost regions. The objective of these studies is to develop a land cover transition model to estimate the evolution of main landform types in the discontinuous permafrost region, investigate effects of spatial temporal thawing driving factors on the land cover evolution, any driving factor that we think these are affecting the rate and pattern of land cover evolution in Northwest Territories, and utilize more advanced statistical and machine learning methodology for modeling these land cover evolution and using this model to predict the future. The study site here in this study is Scotty Creek Research Station, located 50 kilometers south of Fort Simpson. In this discontinuous permafrost zone, areas that are covered by high peatlands are location of permafrost. Permafrost plateaus, bogs, and channel fens are 3 dominant land covers in this region, which are the variable of this study because we are going to model the transformation or evolution of these 3 dominant land covers. In this figure, you can see 4 classified imageries from Scotty Creek Research Station done by Laura Chasmer and Bill Clinton, and we are using these data set for training our time series land cover model TLCM. Our methodology. So this figure represents 3 main steps of developing the TLCM model or time series land cover change model. The first, and I will talk about each step separately. The first step is preparing or pre-processing the data set, which was very time consuming. So we had to pre-process all the data set for finding the main driving factors for developing this model. The next step was developing a generative model, because for time series change or for time series prediction, we needed more data set, and we decided to boost our initial data set by developing a generative model. And the last step is using the boosted data set, a combination of boosted data set and an initial data set, to train a time series land cover change model. So the first step was preparing the initial data. The initial data set is composed of two data set, dependent variable, which is the variable that we are going to predict for future, which are the main land covers, channel fence, bogs, and permafrost plateau. And the independent variables are driving factors of change. Our main focus is try to model the land cover in evolution, spatially and temporally. So this model is a spatial temporal model. We consider some independent variables, which is distance to interfaces, because thaw occurs from the edge of each plateau inward. We choose Euclidean distance of permafrost plateau to fen, distance to fen, distance to bog, and also distance of other land covers to permafrost plateau. So this is a spatial variable. And also we had cost distance to bog, because there is a phenomenon in north discontinuous permafrost region called bog capture, which is about instantaneous hydraulic connection of an entire bog to fen. And also there are 2 other time-dependent variables, which is time horizon and accumulated temperature. I didn't mention anything about the land surface temperature, which is another driving factors of change. We generated this data by using Google Earth Engine platform and using Landsat imageries to calculate the land surface temperature based on the time step that we have in our model. So as I mentioned, the process of implementing the time series land cover model is done in 3 separate steps. The first one was apply a random forest model and multinomial logistic regression or MLR model on initial data set to represent the historical evolution of each land cover. Then we use the best model from the first step. One of them random.
Recording in progress.
Pardon?
Don't worry, carry on. Sorry about that.
Okay. And boosted the initial input data to improve the performance of the model. And after boosting the data, we use an MLR and XGBoost method to simulate land cover change. The second step is about generative model. Why we are using the generative model is that spatial temporal forecasting of categorical data is challenging because the input data is multivariate, and also the data set is not large enough to analyze the relationship between time-dependent variable and categorical output. So to overcome this limitation, we generated synthetic data to represent the change of land cover in Scotty Creek for time step that existed in the initial data set. And after generating this data, we combine the predicted data with the initial data set we have. As I mentioned, we use random forest, XGBoost, and MLR models. Random forest is a type of ensemble learning model composed of parallel decision tree, which you can see here in this plot. And XGBoost is the same, an ensemble learning model, but use a combination of sequential tree to each tree corrects the mistake from previous model.
Shay, sorry to interrupt you, but you've got 1 minute left, so you might want to just kind of try and wrap up your take-home messages, I think.
Okay, sure. So this is the result of this study. The first step, we showed that the random forest model has had a higher accuracy compared to MLR, and we use random forest model to generate data. You can see this is a land cover generated by random forest, MLR, and this is the real data. You can see random forest is performing better than MLR, and we use random forest to generate more data sets and add it to initial data, and then we trained an XGBoost and also random MLR model again on the boosted data set, which shows the land cover pattern change. And we proved that XGBoost model, although outperformed the MLR in terms of being replicated in historical land cover, but MLR captures the correlation between time and a spatial variable better than XGBoost. And this is a time series prediction by MLR over 200 years time step in Scotty Creek Research Station. And for future, we are going to use this model on other case study to see the performance and analyze the effects of land cover change on hydrological features. Thank you.
Thank you very much. So thanks again for finishing on time there. We've got one more speaker, so I'm going to move on to the next speaker. And if we have time at the very end, there may be some more questions. So, so I would like now to introduce Nanar from Wilfrid Laurier University.
Can you hear me?
Nanar?
Good morning, good afternoon.
Yes,
okay, good.
You, yeah.
Okay. So I need to share my screen. Let me see. Okay, I think this is the one. Do you see my screen?
Yes, that's good. Yeah.
Okay. Let me start sharing. Do you see my slide?
Yes, that's good.
Okay. Is it in a good slideshow, right?
Yes, it's perfect.
Just to make sure.
Yeah.
Okay. So good afternoon. My name is Nanar, and I work at NWT Center for Geomatics, and I also do my PhD with Professor William Quinton at Wilfrid Laurier University. And I want to present my work that I did for my course. That's called ground feature extraction from fully polarimetric synthetic aperture radar data. So shortly, we will go through research objective that is for this work, that is done for this work. Also, we'll talk about a little bit of remote sensing. What is remote sensing? What is radar? What is SAR? What is polarization? And what type of data I'm using? And what are the processing methods? And what are the results for this data processing? So, oops. What's going on? Okay. Okay, so the objective of this work is to extract and analyze ground features from fully polarimetric L-band synthetic aperture radar data. And this data will be helping us to increase information content that we derived from a synthetic aperture radar data signal and to solve remote sensing problems such as detecting, discriminating, and classifying ground features. So the work contributes to the studies of permafrost thawing and its impact on the Deitcho region, Northwest Territories, Canada. So the remote sensing, I don't know what's going on with this. Hold on. I'm not sure why it goes like this. This is not right. So the remote sensing is a science of acquiring information about Earth's surface from distance without being in contact with her. And so there are two types of remote sensors. Mainly it's active sensors, which are considered radars, and passive sensors that are optical. We'll talk about only radars in my work. And so this slide shows how radar works, and basically we have a signal that transmits, and two signals, antenna transmits and receives. And the actual timing, between the actual receiving and transmitting and receiving, we can actually compute the range, means the distance. That was the basic goal for the radar. But as it progressed, technology progressing, we're acquiring more and more information from the radar signal, except besides the range, right? And so I'm not sure if I can go just slide by slide. So this slide shows the commonly used radar bands, which are L-band, C-band, and X-band. And so most of the remote sensing instruments use these three bands. And the difference between bands is not only the wavelength, but the characteristics of the wave, depending on the frequency. So some of them can penetrate for instance, as it shows, canopy completely to the ground. Some of them return right from the canopy, and the C-band is just goes up to the middle of the canopy. The area of interest, I'm not sure what's going on with this. Okay. What's going on? Hello, can you hear me at all?
Yes, we can hear you. Yes, we can see you're having.
Okay, something is not right with my sliding. They go automatically. So
well, you have just 3 minutes left, so do your best.
Okay. Okay, basically, I wanted to talk about a little bit of polarimetric data that I'm using in this slide, but let's go on to the actual results. This is the data. This is the data sets that I'm using. This is the area of interest. It's a Scotty Creek in Deitcho region, and so the processing of the polarimetric data sets is basically the objective of this. The objective is to process the polarimetric data sets because the interaction of polarized radar signal with objects on the Earth's surface changes the polarization of the return radar waves and the nature of these changes depend on the characteristics of the objects on the ground. So therefore, using these changes in the polarization, we can identify parameters that characterize a target or the feature on the ground, right? Which allows us to solve a problem of assessing the physical state and properties of the target on the ground surface based on a polarimetric characteristics of the return signal. So for this work, I will use the different types of decompositions, but I will present only a Pauli decomposition, like polarimetric entropy alpha, anisotropy decomposition, and entropy alpha anisotropy decomposition. So basically, this decomposition helped to discriminate key characteristics types such as Bragg surface, forestry double bounds, vegetation types, and surface roughness on the surface of the Earth. So, and comparison with optical images of the final results on a Google Earth revealed that the classes from the unsupervised classification that we received as a result of the processing reflect the major features on the ground, such as vegetated areas, unvegetated areas, water bodies, and marshes. In addition, the polarimetric interferogram was generated, but I don't know if I have time to show it. But this work shows the effectiveness of remote sensing radar technology for extracting ground features and for monitoring ground surface affected by permafrost thaw. So this is the area of interest right now. Shows the polygon on a intensity images for the data, and this is just can I go just by not by slideshow, because it seems like it shows something automated.
Why don't you take it out of screen? Why don't you take it out of presentation mode and just put it on? So
okay, so which one is it? Like this one? Yeah.
No.
Okay. Yeah. Yeah. So this is it still shows this one, but I will go one by one. So this is the data sets that I use. It's only like four images, 4 data sets. They are for June, 2 for June, 1 for August, and 3 for September. So they are called, all those 2 pulsar, they like synthetic aperture radar data taken in full polarization modes. So the polarization, again, we will not talk about this too much because it's not have time. We have no time. So I will just talk about the area of interest, and this is the area of interest, and and processing. Basically, this slide shows the it's called it's called polarimetric signature, which is it's a kind of graphical representation of a change in the backscatter of the signal as a function of polarization. So this is why it's called polarization signature, and it's useful for describing the properties of the target. So particular for the area of interest that we received is this polar response, copolarization response for the area of interest. And just for each pixel, right, we have for each pixel, unbelievable. I can't do this. This is not right.
Just press escape on your keyboard.
Okay, every time I need to click on this, probably, I'm not sure, but even that, it doesn't help though. even that I keep going.
If you press the escape button on your keyboard, it should come out of presentation mode. Oh no, it's doing okay.
Escape. Okay, so show like this. Okay.
Yeah, that's fine. That's
okay.
fine.
Yeah. Okay. I will show it this way. So basically, for each pixel, we received on a radar image, right? And there is a corresponding scattering matrix, and which describes the response of radar signal in full polarization channels. So the elements of this scattering matrix, like it's sometimes difficult to process, but therefore the composition of the scattering matrix is used, which helps to decompose the scattering matrix into components, right? Which has simpler interpretation. Like for instance, cloudy put here decomposition allows to differentiate objects according to the type of scattering mechanism. As to this, there are 3 parameters are calculated: entropy H, anisotropy A, and parameter alpha. So as I showed before, no, I didn't show this. So this is the actual distribution of a pixel in a parameter field of H alpha for the area of interest of Scotty Creek region. So this shows how much we have like water, or moist on the ground, or a dry area, or just a vegetation. So depending on the area of interest, we may have completely different of scattering like a distribution. So for instance, this shows the pseudo color of cloudy Padier decomposition parameters for the data acquired on August 18, 2017. So you will see that A is a parameter alpha, H is an entropy H, and A is an anisotropy A for the same area, right? And when we do actual results of this decomposition as a classes, we can see actually the classes classified the radar image completely like unsupervised classification for the 2 dates, for June 9 and September 29. You can see that the actual differences between 2 dates, and because the actual area changed, something happened between these 2 days. Like, is it like more moisture, less moisture, more dry land, less dry land? You can see the river here is more vegetated here than here. And so it's a lot of information we can actually acquire for this data. And final classification, I don't know how much time I have still, but I want to show the final classification. You can see here that on the right, on the left is the Google Earth, just the Google Earth. And here on the right is an actual classified image from the radar data. You can see here that vegetated areas, less vegetated areas, water bodies, which is completely or completely dry areas, or the areas that have no vegetation and more rocky areas. So this is very quickly, I don't know how much time I have. I can go back to my presentation, but I wanted to make sure that I will cover mainly the actual the results.
I think that's fine. I think we're out of time actually. So
okay, yeah, okay. I should stop doing this presentation. Maybe it's in some kind of automated mode or something. Yeah.
Yeah.
Okay. But that's fine.
Have fun figuring that out. Okay, thank you very much, Nanar, for that presentation, and for all the speakers. I want to remind everybody that this brings us to an end, and I'd like to remind everybody that we have the AGM now, starting at 4 o'clock Eastern time. So please do join that. I'm sure there's lots of important and interesting items of business that we'll be talking about. So We are going to end this meeting now, and you have to rejoin using the same link as you did use for this meeting, okay? And I think I will end it here now so that we can have a little break before we move into that, that meeting. So thanks again to all the speakers, really interesting talks, and look, see you all in 15 minutes for the AGM.